I'm so happy.
Thank you, Matt. I'm glad you are. Today we're going to finish up our discussion about the D word distributed. With definitely with coordination. This is just if you're in a distributed environment, well, how do you coordinate with one another? Hopefully you can tell that there's going to be a lot of different issues, namely how do you lock certain resources and how do you communicate and make sure you all agree on certain properties of your distributed network. So we're going to go into a little bit of that today, and that'll complete our discussions on distributed operating systems.
And operating systems?
No, because then we're going to do real-time systems next, which I could teach a whole course on, but we're only going to do one lecture. Okay, so coordination, let's see, 18, event ordering. All right, make sure, you have to keep in mind the order of events to make sure certain resources are available to one another, mutual exclusion, can things happen mutually exclusively, atomacy. All right, we're going to go through all this. And I never liked this listing of objectives, so we're continuing. All right. So what the book does in order to try and simplify the explanation of distributed content or coordination is they first decide to define this arrow property. Okay, it happened before or requires. Namely, if A and B are events and A was executed before B, then they're just going to say A happened before B. This is just a notation to help simplify the explanation of a lot of different features that we're going to come up with. Also, an important note, it is transitive. So if A happened before B and B happened before C, therefore, you got this, Matt? No? Yeah, A then happens before C, so it's transitive. So you might have a picture like this. Well, you're going to have three different processes, P, Q, R. All this is saying is P1 happened before Q2, Q1 happened before P4. Okay, hopefully that makes at least some sense. And then R0 happened before Q4 and Q3 happened before R4. That's all this is saying.
Why are they drunk driving?
I had that same exact thought, actually. I don't know why they're squiggly like that, but they are.
Like, what are those supposed to be?
Those are the arrows. You know how back here we had straight arrows?
Yeah.
And then you decided to make them curvy.
So
I think there's no reason why they're curvy, correct.
Okay.
Except to make you ask that question. So, what comes next is we have to associate basically all these events with a timestamp. You know, it happened at this time, so then we can say that if A happened before B, then the timestamp of A is less than the timestamp of B. All right, hopefully that's nothing new. Each process does have a logical clock, and it's monotonically increasing. Why is that the case?
What is monotonically?
1.
It's going up steadily as opposed to jumping up 2, then jumping up maybe 1, jumping up 3, then jumping up 1. So it's just steadily going up or increasing.
So
and why is that the case?
Because time only goes forward.
Time only goes forward, right? At least in our systems, we're going to assume that it also goes forward, and in our systems, we're going to assume it's always monotonically. We're not going to play the good old physics game about relative time right now. We're just going to assume everything's monotonic. Let's see. Naturally, it advances the clock. All right, timestamps of two events are the same, then the events are concurrent. Great. We can use process identity numbers to break ties and create a total ordering if we want to. If you number all your processes 0 up, then the lower process. If it happened at the same time, then the lower process happened first. If we wanted to make an order.
Priority one?
Right, we could say the lower number has a higher priority. It just makes it easier sometimes. And then we get a 3-letter acronym that they never use again. So distributed mutual exclusion, or maybe they do. Let's see, this consists of end processes. Each process resides on a different processor. Each process critical section that requires mutual exclusion. If PI is executing its critical section, no other process is executing its critical section. Does that make sense? If there's a critical section, only one process can be in it at a time, or for all critical sections on all processes. All right, so the book's going to do 2 presentations. Okay, good. So they use the acronym again. The centralized approach, basically you have one guy, or one computer that is the keymaster. And in order for you to go into your critical section, you have to grab a lock from the centralized guy. He has to approve it, and once you're approved, then you can go in your critical section, and then you have to give it up afterwards.
So it's like the same exact thing, except it's different computers.
Right, now, yeah, remember distributed, so we have multiple computers. What's the issue with this one?
What if we ask for something at the same time?
What if two people ask for it before he gives it?
Oh, then he just decides who goes first, probably by a priority of computers.
So somebody says, I need a lock. He says, okay, pause. Somebody else says, I need a lock. He still has the lock.
So you have to wait. So
What
if
if
some-
everyone asks at the same
He hasn't
time?
given the lock to the other computer yet.
hold on, say,
He still thinks the lock is okay.
all right, we're gonna have to start drawing pictures. So we have, we'll call them, I like the word keymaster for some reason. So
I do too.
Keymaster.
It's cool.
Okay.
And then we have process 0, that's on distributed system 0.
Okay.
And then we have process 1 on distributed system 1.
Okay.
Okay? Just giving them different names so it's clear what's going on.
Okay. So process 0.
Yes.
Talks to keymaster.
He asks, requests.
Okay, so we got a directed
Requests a
thing
key.
going on.
Keymaster checks to see if he can give a key.
All right, because he still has a lock, right?
Right.
So that happens 1, and then the keymaster has a lock,
I do have a lock.
so he's going to grant it.
Pause.
We have-
Oh, he says.
Process 1 now says, I need a lock. Or, yeah.
Oh, and this guy.
And keymaster says, I still have a lock. Okay.
Oh, I see what you're saying here. All right, request a lock. I have a lock.
Wouldn't it just go in like a queue or something?
Right, there's going to be a queue.
Okay.
These go into a queue. He only requests the first one.
Okay.
So he's going to grant him, and he's going to tell this guy, wait. Yeah, until he returns the lock and then give it to P1. So what's the process? What's the problem here? Now we've drawn a nice picture.
Everyone asked for it at once. That could be bad.
That'll be bad performance-wise, but that's what we want to guarantee is that only one person
Only
can
one person
be in the critical
use it.
section. So we are satisfying that. He just serializes until he's done and then
What
sends it
happens
to
if
the...
keymaster crashes?
Yeah, what happens if Keymaster goes down?
Sadness.
Yeah, so that's the first big
Single
issue.
point of failure.
Yeah, you got a single point of failure.
And then
Which equals sadness. What's the other problem?
What if a process goes down while holding the lock?
Yes. What if he goes down while holding the lock? What's
keep it back up.
Well, how does a keymaster know this guy's down?
Signaling
Continuous
stuff.
Heartbeats, right? Okay. So there is actually a mechanism to help with when a system goes down. You can work that out. There's going to be a significant delay, but you're not going to be in an ultimate sadness where no one can have a lock anymore.
Like
right?
this week.
Like this week. So, and that's usually something to solve. Really, the big problem is you have a single point of failure. All right, and they're saying here, in the book, they say the scheme requires 3 messages per critical section. You request, and then you get a reply from the keymaster saying grant, or another way to do it is you request and then you wait for a reply, and the keymaster doesn't send a reply until you can be granted, and then you have to send back a release at some point. All right. So another way to do it is the fully distributed. If process P1 wants to enter the critical section, it generates a new timestamp and sends that request, my process timestamp, to all other processes in the system. Okay? So we no longer have a keymaster.
We have P3 on P3, or P2 on P2.
Yeah, let's do that. So we have P1 and then P2 on D2.
We should call them R's.
Yar. Resource.
We have R2D2.
Oh, there. There it is.
December 15th.
So in process PJ, so he says, give me lock. This by the way, is the most I've written on this board, so you came in on a good time. Give me lock. We're not going to have articles anymore. It may, not give me the lock, just give me lock. It may reply immediately or defer sending a reply back because it may not be able to have it. It may be in the critical section. And when PJ or PI receives a reply from all their processes, it enters the critical section. So he may reply good, and this guy may wait a while before the reply. Okay. After exiting, the process sends a reply message to say that, hey, look, I'm done with this critical section. Okay. What's the issue with this one?
Somebody could just be programmed up to never give them the lock.
Yeah, well, yeah. If someone goes rogue, you can never give up the lock. That's true.
Again, if the process is down, he'll never receive a reply.
Right, never receive a reply, so you're going to have to
never enter his critical section.
Yeah, that would be bad. You got to somehow resolve that. Although you can set up a heartbeat thread, and maybe you'll have a way to signal that we're just going to assume you're down, so you're going to have to reboot your whole system and then come back up later. So there's actually a way to deal with that stuff. Let's say if he goes down, you're probably going to have another machine or somewhere along the lines that you say, hey, look, this system hasn't responded in 2 minutes. Get rid of him and just grant the lock and then tell everyone else, hey, look, that machine's down. Go ahead and grant all locks from that machine. And then when he comes back up, he'd have to talk to whatever machine and say, hey, look, what happened while I was gone? And then have to catch up from there. So there's a way to get around that single point of failure in this model. Excuse me. Who wants to code this up?
Not me. You can pay me to.
Yeah. Oh, okay, they're going to keep going. The decision whether to process PJ replies immediately to a request. If it's in the critical section, it defers, obviously. PJ does not want to enter its critical section, then it sends a reply immediately. Great. If it wants to enter its critical section but has not entered it yet, then it compares its own request timestamp to the other timestamp. If its own timestamp is greater than the other one, it sends a reply immediately. That's another section we haven't talked about. What if P1 is in the middle of requesting the same lock? So what happens there is this is how we fix it here. If your timestamp is greater, aka P0 requested it before you did, then you go ahead and send the reply and you wait. You clear yourself out and wait for the new replies to come back. So technically, freedom from deadlock is ensured if you're allowed, if you have a mechanism to bring these systems back up if they crash. Let's see, freedom from starvation is ensured since we have that ordering that we talked about earlier where it's based on timestamps if a critical section is going to be granted. Of course, the number of messages per critical section is 2 times n-1, where n is the number of machines.
Cool.
As opposed to the single point of failure where you really had only 2 messages. So for large systems, this becomes very cumbersome very quickly. But it does give you what you need.
We'll just create a central thing that never goes down.
Right. Why don't we just make a machine that never crashes?
Can we call
Or
it
that
Death
never
Star?
gets broken into and goes rogue, right? I mean, simple, right? What's that?
Can we call it the Death Star?
The Death Star. Yes.
Just keeping with the theme.
Keeping up with the theme? Okay. Don't worry, we'll have another section, another opportunity to talk about it when we do the 2-phase commit. Did y'all do 2-phase commit in applied networking?
Yep, might as well just skip it now.
Really? You didn't? You already did it? Excellent. Okay. Yes or no? I'm not believing that face.
You shouldn't.
I'm not believing that face. But we'll call it the Death Star. That's okay. All right. Anyways, coming back. 3 undesirable consequences. What happens? Needs to know the identity of other.
Photon torpedoes.
What's that?
Photon torpedoes.
Photon torpedo. You just.
Did you just like force choke him?
Well, he just, you don't combine those two, right? Don't be doing that. Don't be doing that. All right. Let's see. Process needs to know the identity of all other processes in the system. So if you need to add a process to a distributed system, you need to notify everyone else of that process so they know to request it from every process. One process fails, the entire scheme can technically collapse. And this is what I tell you about. You can be dealt with continuous monitoring of all processes on the system. Somehow having other machines be able to do that will be good. Processes that have not entered the critical section must pause frequently to assure other processes they intend to enter the critical section. AKA, if you're happily computing, all of a sudden you get a request, you got to stop what you're doing, service the request, and then go back. So there's a little performance cost there. But you do get rid of servation and deadlock. All right. Anyone? So another approach, I was going to ask if y'all can guess another one, but is a token approach. You have a token. Here we go. This is where it starts to get interesting. You have a token, and whoever has the token or possesses the token entitles the holder to a critical section. So now your processes are going to feel entitled, which is okay. You organize them logically in a ring structure. All right, so they may not be connected by a ring, but you have a channel, so to speak, like this. And that's your ring. They may be hooked up to a bus or something, or Ethernet, but we're just going to say they're in a ring. So unidirectional guarantees freedom from starvation. That should make sense in a bit. Is this the only slide on this?
Hopefully.
Oh, wow, that's amazing. All right. So, if P0 wants to execute the critical section, they send a message, give me token, signed P0, right?
XOXO.
Yeah, XOX, right. And then P1 says, I don't have it, send it along. And P0's like, oh, I have the token. Has to decide whether to finally send it, and then eventually goes back to P0. So, you'll see what's going on here? Every time you want it, you have to do a full loop around in the ring, but it's a lot simpler. Whoever has the token is able to do it. So, what? Oh, 2 failures, lost token. What if someone loses the token in transit? What can you do?
The first person that sent a message gets the token. When the message gets back to him, he says, okay, I've got the token.
Oh, okay, I like that scheme actually. It's a lot better than the election, which is like, all right, we have to hold an election, which is literally everyone voting on who should have the token, and whoever gets the most
I
votes
vote for myself.
has the tokens, right? Okay, that's another. Well, that's why I don't like election. What do you do with ties? Well, I guess you would then go to whoever's the lowest number, right? D0 if there's a tie between D0 and D1.
No. That's distributist.
But processes don't have feelings, Chris.
Threads do.
But they hold elections.
You could hold an election without feelings.
Election is totally based on
How do they
feelings.
have a right to vote if they're not people?
No, I didn't say anything about a right. They have an entitlement to
Oh,
vote.
so an election is called and the American people vote on with.
So does this work in like China?
Can I just say no and then move on? Because all right, what happens when this, let's say P2 dies?
Then the communications path is broken.
Yeah. So what do you need to do?
Make a new one.
Yeah. Then you just hook it like this until it's done.
Well, that's a pretty simple one.
Yeah. Well, there's probably about 20 of these, and I didn't want to draw them on the board because that's too much work. All right. Anyone see an issue with the token-based approach?
Yeah, computers can't vote.
Yeah.
How about performance-wise?
Circle, circle, circle.
Circle, circle. Yep, you gotta do a full circle just to get the critical section. All right, and that's all we're gonna talk about. Great. Which one do you think is implemented? Oh, this is gonna be good.
Centralized.
Anyone else?
Is that one too?
No.
None of them.
It depends.
I'm glad. Okay, those are the 2 best answers always. Either none or it depends on
We
operating
cached
system.
it.
Or we cached it, right?
We
Token-based was actually implemented for a long time, and then people decided, well, you can have we're just going to do it one of two ways. Either ignore the problem, or you're going to have a hybrid, literally a hybrid, between this distributed version and the centralized version. So what you're going to do is, you have maybe 20 groups or 20 computers, you break them up into 4 groups, and each of those groups has a commander or a leader. And then inside that group, they implement, commander, they implement the distributed model. And
I
then-
think this class would be like 20 times better if you just threw in cool words like that with everything.
Gold leader, red leader,
Gold-
red 5.
At least in the distributed sense, right? Okay. So moving on, the book's going to go into a different term now. So kind of changing gears a little, but not too much. I can never pronounce this word.
Atomic City.
No, it's atomicity, whatever. Atomic-ity, I don't know what.
Atomic ID.
Atomic-ity, I don't know what they're trying to say here. Atomicity? All right, anyways. You basically say you have a group of operations, and they either all occurred or they all didn't occur. You can't stop somewhere in the middle. That's how a group of operations is considered atomic. So to ensure this atomic property, I think it's a lot better. Atomic property of atomicness.
Yeah.
Require some type of transaction coordinator, which is responsible for starting it, breaking it into sub-transactions that can hopefully be rolled back if there's an issue, and then coordinating the termination, which may be either committed or aborted on all sites. And now we're going to talk about the two-phase protocol. Now, seriously, have you all not talked about this one? Okay. If you don't learn anything about distributed protocols, please just learn this. This is probably the most important factor, because this is how
So this will be on the final.
this will be on the final. Thank you for the translation. All right. I'm just going to erase all
And
this.
all other things won't be.
This will definitely be on your final. All right, very common case. Let's say you're at an ATM, right? And you want to, well, maybe not ATM. Let's do this differently. Let's you're on your
Less things
computer.
I have money.
You're on your computer and you want to transfer money from, your American bank account to your Swiss bank account. Just something we always do every day.
Funnel our funds, yeah.
Yeah, what else would we do? So, you have your user. Always a stick figure, because that's about as much artistic ability we have. And we want to send in the request. Well, your bank, which we'll just call the Death Star, because that's what you wanted, needs to communicate. And actually, it's not even this bank. Let's say there's a third bank. Well, your bank actually has it, but he needs to do the transaction in an off-site location. This is where your money currently resides. What do you want to call this one? Nothing? Okay. Call it your bank.
It's a secret. People can't rob it if they can't find it.
Your bank. Completely separate machine, separated by, I don't know, a couple states, right? Maybe it's in a different state. And
Galaxy?
Far, far away.
And then, your Swiss bank account is in a different
Switzerland.
Galaxy bank account. All right.
Far, far away.
Bank far, far away. Perfect. I think we're getting the right idea now. Okay. Request transfer of money. So in order to do that, he needs to deduct that amount from your bank and then add it to the Galaxy bank that's far, far away. Correct? All right. What's an obvious issue that can happen here that you would not want to have happen?
The Death Star gets blown up.
Yeah.
So one just, I don't know why I didn't think of that.
Or if the galaxy far, far away gets blown up.
Blows up to Galaxy blows up. These are all actually great examples of how this solves a problem. Your bank actually.
Preferably they have a backup of that before you did the transaction, and then your bank blows up.
Okay. All right. So the real issue that you haven't talked about is what if you deduct it from your bank account and then the Death Star blows up?
Right.
No one wants that to happen, right?
No.
So, what?
No.
No. So deduction plus the Death Star blows up. I'm going to turn that into another acronym.
Who doesn't like acronyms?
Who doesn't like acronyms? All right, Death Star blows up. Okay. This is not what we want, because then you just lose your, I don't know, however, all your money from your bank account. We need to fix this problem. That's what the two-phase commit does. And the idea behind it is when you put the request, the Death Star basically puts a prepare statement everywhere saying, are you able to do this? And it waits, and each entity within it, in this case we just have two, says, I am ready to do it, and I've recorded that this is probably going to happen. And then the Death Star decides either commit or don't commit afterwards. Exactly. So let me make sure I said that correctly, or we'll explain it again with the slides. First off, it assumes a fail-stop model. If at any point someone here fails, the whole transaction is aborted and uncommitted, except for once you get to a certain point.
So what happens if Death Star sends out the, hey, your bank, get ready to deduct money?
Yes.
Okay, I'm ready. Galaxy says, okay, I'm ready to add money. Death Star sends commit, but Galaxy blows up.
So it sends the commit, Galaxy blows up. When they rebuild the new Galaxy bank, they're going to have to talk back to the Death Star, and the Death Star will say, this transaction, you were supposed to commit it. I love this explanation. When the protocol is initiated, the transaction may still be executing on some local sites. Right. Okay, the protocol involves all local sites at which the transaction is executed, of course. And then they have an example using letters and subscripts that I think are a lot better with Death Stars and Galaxies. Okay, so C1, hold on, I see the sender.
CI.
Let T be a transaction initiated at site S sub I, and let the transaction coordinator at C1, so C sub I is the Death Star. And the site is somewhere.
SI is you.
Is me, yeah, we're SI. We'll just say that. Okay, great. So C1 adds prepare to the log. All right, this is the most important trick. The Death Star has a separate connection to a reliable data storage.
Ooh.
This is the trick. This is the problem. So they have a reliable data storage that's not part of the Death Star, because we all know it's about ready to happen. It's probably, RAID 1+0, and it has backups all over the universe or something, right?
Yeah,
So
it
it may
does.
have other backups elsewhere that are keeping a copy. So this is the reliable data storage. RAID 1+0. And what would this be in Star Wars? What was reliable and never got blown up? Did anything not get blown up?
Yeah, Chewie.
Chewy.
Coruscant.
I like Chewy. I don't even know how to spell it.
But he couldn't tell you the data after you gave it to him.
No, he would write it down. But Han could always understand Chewie.
Han got
So we have a
snapped.
single point of failure.
You just find another
Han
Han.
dies.
But Yoda
It's
can
over.
figure it out as well, and Yoda's now a ghost, so he can always come and talk to Chewie.
Okay.
Plus, Chewie can communicate with his other. What was the race again? I already forgot. Wookiees, thank you. Other Wookiees, and make sure it's okay. All right, we're doing great. So the Death Star is going to talk to Chewie. This is getting better and better. So he adds to the log. So this transaction, T sub I, is held by Chewie right now, and it's in the log, and the status is prepare. It's preparing it. Okay, we're currently preparing it. When a site also is going to, these are also going to receive a prepare message. Whoops, that's the weirdest T I've ever drawn. All right. When a site receives it, he determines if he can commit the message. They're just determining if they're able to do it. AKA, can your bank subtract that amount of money? It's going to reply yes or no. If he replies no, the Death Star tells everyone to abort the transaction. Same thing here.
It's a trap.
It's a trap. If anyone replies no, the Death Star aborts the transaction. This is what I mean by fail stop. If anyone fails to communicate back within the correct time, the Death Star again aborts the transaction and tells the Wookiee to go ahead and delete the prepare transaction. All right. So if no, record to the log and correspond abort. So actually you can tell the Wookiee that T sub I is now aborted, is what's going to happen. Okay. Also, a couple things in mind. If the Death Star goes down at this moment, Chewie says it's still in the prepare statement. When the Death Star comes back, because you know it's going to be built multiple times, it does abort to all the transactions because he went down. He has to stay up the whole time. All right. This is the trick. Force all log records into stable storage. This is what data reliable stable storage is. Okay. Then, what happens next is, let's see, send to C1. So then what happens, the Death Star says, once he gets yes from everyone else, he tells Chewie that we're now in the ready state. And that concludes phase 1. Nice.
Darn. That was, it failed me.
Wait, hold on. I think I skipped a step here. Hold on. Send ready message to C1. That's the death. Oh no, that's what all these people are saying. They're replying yes, which means ready. Hold on. And then this doesn't go from ready, it goes to commit, right? Yes. Then once this happens, the Death Star tells this guy commit or abort. If it's abort, then obviously everyone's going to abort. If he's commit, then that's saying that all these guys need to commit the message at some point in the future. Now you're on to phase 2. Phase 1 has happened. Phase 1 concludes with Chewie either holding commit or abort for your transaction. Now, once Chewie has the commit, all these guys can go down, but when they come back up, Chewie, which actually has a record of the T sub I, what needs to happen to minus from this bank and add to this bank, can always send back the message of what they're supposed to do at any moment. So the only thing that has to happen now is that the Death Star needs to go in and communicate that, hey, look, go ahead and just send out commit T sub I. Once the record reaches stable storage, it's irrevocable. aka once it says commit, you cannot revoke it. It has to happen. Even if some failures occurs, it's going to happen. So it sends a message to each participant informing them of the decision, and then they take the appropriate action locally. All right. Does this make sense?
Yes, the Death Star.
The Death Star. Really, the most important thing is you have this second offsite reliable data storage. That's the key, because if this somehow gets deleted, bad things are about ready to happen because you're going to have to try and figure out what's going on. But that's the trick. And usually this is a very serious data warehouse in multiple locations in the US or the world. Okay. So let's see, site failures. We actually talked a lot about that. If he goes down before he receives a commit message, he can tell the Death Star that I still have this prepared, because by the way, each of these prepare statements are also written into a permanent storage. So when they come back up, they're like, hey, wait, I still have this transaction. What happened to it? And then Chewie can tell. Same thing with the Galaxy Bank and the Death Star. Otherwise, if it's an abort, then you just undo it and then they just clear it out. Okay, great. Any questions?
That last part, do each of the, say your bank and the Galaxy, do they have their own secure storage?
They do not, no. So they could actually lose it altogether. And let's see, how is that one fixed? Hold on. So the way that's actually fixed is that there should be a, hold on, log contains record, in this case executes undo, contains abort on right. Contains ready T, consult C1. If C1 is down, it sends a query status, log contains no control, in this case the site executes undo. Oh, it doesn't actually tell you what happens. It's in here, one moment. Contains a commit T record in the log, and the T must be committed, obviously. Do not contain the record, and then failed cannot decide to commit rather than wait for C. It's preferred to abort T. All activities have. Okay, so what they're saying here.
Always better to abort than to.
Right. Well, that's kind of lame because they just said it's irrevocable and then they just explain the situation where it can be revoked. Okay. So the Death Star, once it's been committed, it's also waiting for the replies from all these guys, right? What it's saying is that if this bank goes down and the prepare statement is lost forever, he's going to say, I can't find the prepare statement. The Death Star is going to go over and say, he can't find the prepare statement. Abort, is what this slide is actually saying. I would assume that Chewie would actually have the prepare statement that was supposed to happen and send it up.
Does not contain the record in its log. Failed coordinator. I don't think that's what it's saying.
What is it saying? If some active site does not contain the record ready in its log.
So he's going, but no, this is the case where the Death Star is down.
Right.
The bank is, your bank is ready.
Mhm.
It tries to query the Death Star, but the Death Star is down. So
Okay.
it sends a query to the Galaxy.
Right. Oh, okay.
And the Galaxy did not contain a ready record in its log. So
Oh.
if it didn't, then we
Then it would
assume that
know.
nothing happened.
Right. Okay.
So we abort.
Okay. So it's saying, yeah, there's another way to figure out what happened. Okay, great. Good. Okay, good. So it doesn't abort. I didn't think it did. In this case, we must wait for the coordinator to recover. Sure. Naturally, this transition is blocked until the Death Star comes back up. That's what you get for dealing with the Empire. All right. Any other questions? This is how it's actually implemented with banks and for most important transactions. This is what they do. They go through every step of this, every single time. That's why sometimes it takes a while for the transaction.
3 to 5 business days.
Yeah, that's a separate issue. That's more legality because this should only take at most a minute, right? But that's something different. That's the fact that they, what most banks do, just due to history.
We're really going to go over banking law now?
Well, you did this. Is they actually store all their transactions until the end of the day, and then they coordinate them. And that may take a while. It may take them a couple hours for all those coordinations to go through. So they just bundle them up and do them. I don't know why they don't do them online, but that's just how they do them. Now, why it takes 3 to 5? Well, because each time you do a step, that's a day. All right, anyways. Okay, so that was the two-phase commit. You will see that on the exam. I will probably ask you if we're in this state with, I'd love to use the Death Star, that'd be great. In this state, and this happens, what do you do next in the two-phase commit? Is what you're going to see that question. All right, concurrency control. They don't tell you why we're doing concurrency control. Okay. Modify the centralized concurrency schemes to accommodate distributed transactions. Oh, okay. So instead of having one in flight, you might have multiple. This shouldn't be that difficult. Global transactions execute on several sites. aka Chewie is going to be able to store a lot of this transaction information. So two-phase is distributed. Well, we have non-replicated scheme. Each site maintains a lock manager and unlock requests for the data items. Hold on. We can use a two-phase locking protocol in a distributed environment by changing how the lock manager is implemented. Sure, instead of having the Death Star, everyone's going to be able to lock it themselves. In the non-replicated scheme, each site maintains its own lock manager, right, with administrator's lock and unlock requests for those data items which are stored on the site. Right. So in other words, each of these guys, you might have a whole bunch of them, are going to have all the locks that could possibly be requested or held. And then they have to communicate to each other who has the lock. This can be more complex with deadlock handling because if a site goes down and you're trying to request something from them, that can be deadlock. Single coordinator. Didn't we just talk about this at the beginning of class? Same thing as beforehand. You have one guy, maybe the Death Star, or the key manager that has the lock for everything. Naturally, you have a bottleneck. Okay. Anyone need this picture before I erase it?
It's pretty cute though.
You like it? Yeah.
Rip.
All right, then there's the majority protocol. P0, D0, P1, D1, P3, D3, P4. Hey, he gets a circle. D4, and we'll go back to the square. P. Did I skip 2? I totally did. P2 will be down here. All right. Majority protocol. Someone wants to have the lock. Did they actually go into the steps? No. All right. Someone wants the lock. P1 wants the lock. Everyone votes whether he gets it or not. And if he gets the majority, he wins.
What do they vote based on? What do they vote based on? Favoritism?
Basically. Avoids drawback by dealing with replicated and decentralized. Right. More complicated. The idea, this deadlock can occur in locking only one data item. This is very complicated to implement. We're not going to go into the implementations of this, but again, you have a copy of all the locks. And if P0 wants the first one, obviously he's going to vote for himself, and then he's got to ask everyone else for it. If he wins the majority of it, the reason for this is, let's say that P2 is in the critical section of executing what P0 wants to lock for. He sends out the request. Due to how the algorithm works, it may be the case where everyone else votes yes except for him. In that case, P2 has to roll back out of his critical section and give the lock to P1, to P0. All right? That's what it's saying in this case. This implies some type of preemption. Well, technically this one's non-preemptive because if he's in his critical section, he has to roll all the way back. He can't restart in the middle of his critical section. The bias one is similar. But shared locks prioritized over request for exclusive locks. So if you're sharing a lock, which means that, let's say you can have it to where these two can have a lock at the same time, then it's okay.
Sounds pretty communist.
It's
to me.
very communistic. It's not, this is actually kind of complicated. And you'll probably you will not see this on a final exam. Unless you take advanced operating systems, then you're probably going to see this. Again, deadlock is, but if you want an exclusive lock, then it's handled just like the majority. All right. Yeah, the point of this one that they don't say in the slides is that if he's in the middle of his critical section, since they can share the lock, there's a mechanism for him to not have to roll back all the way. Okay. Primary copy, we're not going to go over primary copy, but timestamping is important. Hopefully you can see that it's very important to come up with some type of unique identifying for every thing that occurs within a distributed system. So you need to come up with a unique timestamp. And since this is distributed, it is possible that two processes could create a timestamp that have the same number on them because it's concurrent. Can anyone think of a simple way to fix that? Say P0 creates a timestamp, and we'll just say it's 1, 2, 3, 4. and so does P1. So those timestamps are not unique because they're the same. How could we guarantee their uniqueness?
And the PID.
Add the PID. All right, right now I've been nice in numbering them 0, 1, 3, 4, and 2, but it may be possible there's a process 0 on D0, process at 0 on D1. But you're close. Instead of using the process ID, you can use the distributed ID. Yeah, so this would be D0 or just 0, and then this would be D1, and then you append it like that. All right, now it's unique.
Awesome.
Site identifier. I called it distributed identifier.
And they put it at the end.
And they put it at the end, I put it at the beginning. Yeah.
Pending.
So you're right.
This is probably a lot easier because if you want to see if who has higher priority, you just do strictly less than, and then you're good to go. So this makes a little more sense.
No.
Yeah, because if the 0 is over here.
But humans read left and right. What in America we do.
All right, deadlock prevention. Hold on, let me stop here. I've recorded for way too